Hi everybody. This one is the electronic packaging system. Um, what I'm going to do today, I'm going to review about the transmission line. That's the in the chapter of chapter 3. Okay, from my book. Actually, this one is about circuit analysis. You already been through the transmission line before, but this one just the review. And then we're going to talk about the transmission line more complicated later on. As you know that, let's see, in your integrated circuit, you are going to dealing with a transmission line. In the case of this one, my code strip line, you have a metal contact, and you feed your signal in, and then you have a grounded. Whenever you have the positive and negative, or you feeding a signal in to the system. That means you are dealing with transmission line. Before we go through the transmission line, let's take a break. Look at the circuit analysis. For this lecture, I have totally 5 pages. And you're probably familiar with this one about the circuit analysis. We're going to talk about a series RLC circuit. And the topic 3.2 from the book, the analog method of analysis. That's the page number 57. You have the source voltage EI, and you have our RLC connected in series. And let's assume that the I is also time dependent. That's the source voltage. EI equal to EA exponential j omega t, where omega is the angular frequency, that's the 2 pi f, where f is the frequency. And EA actually is the amplitude of the voltage, and that's the time dependent. That's why you have t here, and you also are considered about the phase because you have j. Also I, the current flowing through the circuit, which are the same as the current flowing through L, R, and C, because this is the series circuit, and that's according to equation 3.2 from the book. Now let's take a look voltage drop across L, across R, and across C. By applying Ohm's law, you have for voltage drop across R, your ER simply equal to IR. And this is straightforward because the current is equal to IA exponential j omega t. Now when you're dealing with inductor and capacitor, you're getting more complicated system. Sorry. So what is your EL? I actually wrote down our EL at the end equal to j omega IAL exponential j omega t. And if you are looking for the magnitude of EL, or the voltage drop across the inductor, it simply become omega IAL. Let's take a look at the derivation, the voltage drop across the inductor. You start from EL, you know the property EL equal to L di by dt. And you already have I equal to RA exponential j omega t. So you just differentiate. You end up with j omega IAL exponential j omega t. According to equation 3.4, in the book. Next, the voltage drop across the capacitor, C. You end up with EC equal to negative j IA over omega c exponential j omega t. Well, if you're talking about impedance, you can see that R is the term the frequency independent, where the inductor and capacitor are frequency dependent. For L, you can see that your impedance is the what? Omega L. For the frequency is higher, you have a higher impedance. That's the opposite or reverse of your capacitor. This is your capacitor impedance 1 omega C. For the higher frequency, you have a smaller impedance. So it's very opposite the way around. Just to point this one out for you. What else we have here? Well, as I mentioned before, if you want to find earlier the magnitude of the voltage drop across the capacitor, you simply take IA over omega C, and this one actually become agree with Ohm's law, V equal to IR. Okay, so your R, or in this case is the impedance, equal to 1 omega C. And for inductor, you have impedance of inductor is equal to omega L. Okay. Now take a look at the series circuit. You apply KVL, Kirchhoff voltage law. The source voltage equal to the voltage drop across resistor plus the voltage drop across inductor plus the voltage drop across capacitor. And you add all terms together, you end up with the real part and the imaginary part. That's give you the phase of the circuit of the signal. So you have the real part, you have imaginary part, and this one is also agree with Ohm's law. E equal to I, and then Z, that's the impedance. So your total impedance actually is equal R plus J omega L minus J 1 over omega Z. And then you can also find zero equal to this one, this term. Now take a look at the plot. You have our x-axis as the real part, and the y-axis is the imaginary part. You have R right here, and you have omega L minus 1 omega Z. And this is the Z plane. That means the impedance plane. And you have the phase angle, that phi. And this is your vector of the impedance. Now you can also look for the phase angle phi. You simply look for tan phi equal to imaginary part, or y-axis, right? Divided by real part. That's the x-axis. And you end up with the omega L minus 1 omega C divided by R. And your phi simply become arctan of omega L minus 1 omega C over R, according to equation 3.12 from the book. Then by applying Ohm's law, E equal to IR, this is your I, and this is your R, total impedance in the circuit. In this case, it's the series circuit, RLC series circuit. Now I'll take a look at the problems 3.3 from the book. For the circuit shown in figure 3.3, as you were to determine A, the impedance, total impedance, B, the voltage drop across the inductance, C, the voltage drop across resistance, and D, the voltage drop across capacitor. This is your circuit. You have the source voltage EI with the amplitude is 10 volt and the frequency is 10 kHz. This is your L, 20 microhenry. R equal to 100 ohms. C equal to 15 picofarad. Okay, let's start with the total impedance. You know that this is your series circuit, so the magnitude of your impedance, total impedance, equal to R squared plus omega L minus 1 omega C squared to the power of 1/2. So you just plug in number R, L, C. You end up with your Z equal to 9.98, 10 to the 4th. That's way high. Okay, I don't think I did not do something wrong. 3/3b, the voltage drop across resistance, E equal to IR, and the magnitude of the current, or the amplitude of the current, that's equal to 10 volt, and you already have R, so you divided 10 volt by 9.98, 10 to the 4th, and then you also are multiplied by your R, the resistance. You end up with the voltage drop across the resistor is 10 millivolt. Next, 3/3c, the voltage drop across the inductance, EL. Where EL, the magnitude equal to omega RAL, just plug in number. You know that the frequency is there, 10 kHz, that's the 10 to the 4th. You end up with the voltage drop across inductor is equal to 0.13 millivolt. The last one, 3/3d, the voltage drop across the capacitor is C. This is the magnitude of the voltage drop across the capacitor, IA over omega Z. You plug in number, you end up with the voltage drop across capacitor equal to 106.32 volt. Okay, so that's all about our RLCC circuit. Now let's move to the transmission line, and you have studied that before, at least in electromagnetic field and wave. Let's summarize about what's going on with the transmission line. This is your transmission line. You have the source voltage, and you have the source impedance, ZS, and you have the load impedance, ZL, and you have a characteristic impedance, Z0. This is the constant. Okay, I have everything just right here. The impedance is have the unit in ohms. When you work on a transmission line, this is very important because for applications, you don't want your input signal to be distorted when you connect your transmission line to any loads. In this case, it can be a capacitor, it can be an inductor, and it can be a resistor. Sorry. Well, Z0, you can take a look. This is the characteristic impedance of the transmission line. It doesn't matter how long is your transmission line is, your zero is still the same. So this is the unique about the property of a transmission line. Your goal is that you want to match impedance. In this case, it means that you try to make a ZL equal to Z0, so you have no reflection from the load end. Okay, you want the right signal. You want to have the clean signal at the load end. Well, that means you want to the reflection coefficient to be 0. By the definition, at the source, your reflection coefficient as the source, you have subscript S, that's the stand for source. equal to Zs minus Z0 divided by Zs plus Z0, and that's equal to Vb over Vf. What is Vf? Vf is the incoming signal from the source, or the forward voltage, and then at the load end it will reflect it back. So Vb, B stand for backward. That's the ratio of Vb over Vf. That's give you where tau is. Tau, or deflection coefficient. Number 2, take a look at the load N. It's similar to at the source. So your tau L, the reflection coefficient at the load, that's equal to ZL minus Z0 divided by ZL plus Z0. And of course that is equal to Vb over Vf. Let's take a look at that special case, or the worst case. 2.1, for the open circuit, that means you have ZL to be infinity. And your tau L, and you apply this equation, your ZL equal to infinity. So you ignore Z0 and Z0. You end up with tau L equal to 1. That's equal to Vb over Vf. So Vb over Vf, if you take a look at the plot, you have forward voltage, or incoming signal into a transmission line with the amplitude A, and the load N is reflected back with the amplitude the same, and a positive voltage. So at the load N, incoming or the forward voltage will add up with the reflected voltage. That's give you a double of the forward voltage, or in this case it become 2A, and that's something that you don't want. You just want, your backward you don't want any backward voltage, or Vb equal to 0. That's what we call the mesh impedance, ZL equal to Z0. The other case is short circuit, ZL equal to 0. Okay, you shorted circuit at the load N. Your tau L is equal to ZL minus Z0 divided by ZL plus Z0. Since your ZL equal to 0, you end up with tau L, the load reflection coefficient, to be negative 1. So that's even worse, because Vb equal to negative F at the load N. Your Vf plus Vb, that's give you 0. So you have no signal at all at the load N. Actually, you expect to have a signal at the load N. And later on we're going to talk about arbitrary load impedance. In this case, your ZL can be either a resistor, inductor, or capacitor. Okay, this is the last one. I don't want, I'm going to break my lecture about the transmission line in many series, so it's not going to be too long. Well, when you're talking about what looking for in the term of the transmission line, how it's work, and what is your goal. Now let's get into the transmission line theory. In this case, everybody know about the transmission line equivalent circuit. It's look like this. When you have the length of the transmission line, or dx, and you have distributed parameters, L prime, R prime, C prime. What does it mean? L prime, R prime, and C prime. Where that's become the unit per meter of that devices. So your L prime actually is equal. The unit is the Henry per meter. Your R prime is ohm per meter, and so on. And at this point you have the voltage of xt, and this one you have the voltage as the Vx plus dx. You have our C prime, you have G prime. That's their conductance in the unit of mole per meter. From distributed parameters, you also know that you can look for characteristic impedance, which is very important because there is play a vital role in your like transmission line circuit, because you want to see that it have any reflection from the load in or not, or from the source or not, because you are dealing with Z0. That's why you need to look for your characteristic impedance in the term of L prime, R prime, C prime, and G prime. That's Z0 equal to R prime plus J omega L prime divided by G prime plus J omega C prime to the power of 1.5. For the special case, a lossless line, you have no loss, so your R is about 0 and it's about G is about 0. So you end up with your Z0 simply equal to square root of, prime missing. This becomes square root L prime over C prime. The next one is very important as well, propagation constant lambda. You have lambda equal to R prime plus J omega L prime multiplied by G prime plus J omega C prime to the power of 1.5. Is very similar to equation to find Z0, but actually instead of two terms divided, but you multiply two terms together. Of course, you have a J term and you have the real part, so you end up with the real part plus the imaginary part. This is the propagation constant equal to alpha. Alpha, the real part, is the attenuation constant. Attenuation rate. This means when you feed a signal into the transmission line, the amplitude of the voltage tend to decrease according to the exponential term. So you have your Vx there when you get into the transmission line. The amplitude of your voltage is proportional to exponential negative alpha x. And if you have no alpha or alpha equal to 0, your V0 still stay the same throughout the transmission line, so no attenuation. So that's why alpha is also very important. But for the lossless line, you have no alpha equal to 0, and your lambda, and B also is the phase constant. Alpha has the unit of neighbor per meter, and beta has the unit of radian per meter. That's the phase. What is the phase difference between the output and the input? So you can look for the beta when you have signal getting into your transmission line. For a lossless line, your lambda equal to alpha plus j beta, but you only have an imaginary term, so your beta equal to omega square root L prime C prime. So your omega over beta equal to 1 over square root of L prime C prime. Omega is the 2 pi f, and beta simply is 2 pi over lambda, when lambda is the the wavelength, right? If you're talking about light. And from the definition, you end up with omega over beta equal to f lambda. That's equal to v, right? V is the signal velocity in the transmission line. That's equal to 1 over square root L prime C prime. Okay. For the next video, I'm going to show you more example. We're going to solve problems together, so make you more understanding about what's going on about transmission line. Okay, that's all for now. Bye.